This video is on section 7.2 of your textbook. It's all about atomic spectra and the way that light and atoms interact. So we're going to start back around 1800 and look at some interesting experiments by these folks, Wollaston and Fraunhofer. Now they did these a little bit apart. So what Wollaston did is he took a really high quality prism in a very dark room and he focused that light and onto the prism, and he spread that out a good ways away against a wall. Now prior to that, even up through the time of Newton, everybody had done work with prisms and seen what we call a continuous spectrum. So one color, the reds here, bleed into the green, the yellows, the greens, and the blues in a continuous fashion, so there were no breaks in the color. But what Wollaston discovered when he spread out the spectrum was that in fact there are these dark lines that occur in the middle of the spectrum. Fraunhofer later did the same thing with a much better prism, and he was able to get a detailed listing of all the wavelengths where these little dark bands occur. And these little dark bands are then named after Fraunhofer. They're called the Fraunhofer lines. And they're present anytime you pass sunlight through a prism. We don't normally see them because they're too small to be seen unless you have a really good prism and you spread out the light really well. So that was really curious, right? Why would there be these dark bands? Where are they coming from? It looks kind of like a barcode. What's going on here? So it was a real mystery at the time. To help with the mystery, here's some work done by somebody whose name might sound familiar to you. German chemist Robert Wilhelm Bunsen was working with collaborating with physicist Robert Kirchhoff, and they developed this system. So Bunsen was interested in looking at the light that's emitted from flames. And he designed a very special burner, one that you might be familiar with, called the Bunsen burner, to give a very clear, colorless, almost colorless flame. So it's very pale blue. And into this flame, he would burn different samples of material. In particular, he was interested in samples that contain only one kind of element. He would then use a telescope to focus that light into a prism, and then he would use this telescope to look at the different lines, to look at the light that was coming out of that prism. And by rotating this telescope around different angles, he was able to measure the number of degrees and quantify where those lines occur. So here's a schematic example of what's going on. So here's the Bunsen burner up here, and if you put sodium into this flame, you'll get this characteristic yellow-orange color. That's the color that we normally associate with logs burning and candles burning, that nice warm glow. And in fact, that yellow-orange color comes from the sodium in those flames emitting light. So if you take that light and you pass it through a slit and then through a prism, and you let that light spread out, what you'll see is for sodium you get two lines only, and they're really close together, spaced very close together at these two wavelengths. And so those two lines, it turned out, matched up exactly with a couple of lines that were here in the Fraunhofer spectrum. So a couple of these dark lines exactly match in wavelength these two yellow lines from sodium. Now Bunsen put lots of different kinds of materials into his flames, and he discovered that in fact you get different patterns of lines from different elements. And in fact that forms the basis for helping to identify certain types of elements. There used to be a test that one would do in a laboratory called a flame test, where you would get your Bunsen burner and take a small sample of some salt dissolved in the liquid, and it would give off a color that was characteristic of the metal that might be in that salt. So you could tell if you had sodium or calcium or potassium, different metals, depending on the color that they give off in the flame. There are other ways that we can look at colors that elements give off. So these things are called gas discharge lamps. And what you do is you take a glass tube that's sealed at two ends with some wires and little metal plates sealed into the ends, and you pump out most of the air inside that container. And then at low pressure, you're going to put some gas like hydrogen or helium or neon. And then you push this across a really high voltage, 120 volts, 240 volts, something really high. And that really high voltage will then cause the gas inside these tubes to start glowing. So these are hydrogen tubes that start glowing. You guys are probably familiar with neon lamps that give you this red-orange glow if we fill the gas inside this tube with neon instead. Now if we take that light and we pass that light through a prism and we spread the light out using that prism just like we would with other colors, then this is what we see for hydrogen. So the light that's being emitted, that's why this is called an emission spectra. So spectra just means to spread out. Actually, this would be one spectrum. Spectrum is singular. Spectra would be plural. So this is one emission spectrum. Emission means to emit light. And so that's what these gas discharge tubes are doing. They're emitting light. They are glowing. So I'm going to draw some wavy lines coming out with little arrows indicating that light is being given off. So it turns out for hydrogen, when you pass it through a slit and then through a prism, what you'll notice is that there are these narrow lines, only these 4 or so narrow lines occurring at very specific wavelengths. And that's very different from the characteristic line pattern of helium or of neon. And so these different line spectra characterize the different elements. Now we're also going to look at a different set of experiments that were done kind of early on. So if you have a source of light right here, and you have a sample of your gas, so we have a tube that we've now filled with hydrogen or helium or neon, and we pass the light through the sample, and then let that light go through a narrow slit, and then through a prism, and then we spread out that light on a screen so that we can look at the colors. Here's what you see. So down below, here is what we see for hydrogen. Notice there's a dark line right here, and then all of the colors of the rainbow that we would expect, and then there's another dark line here, another dark line here, and so on. Now if we match this dark line up with the emission spectrum, we would notice that this wavelength of this red line occurs at exactly the same place as this dark line right here. And the same thing happens when we look at the absorption spectrum of helium and the absorption spectrum of neon. So we can kind of rationalize what's going on here as we pass the light through the sample. Some of the colors of light are being absorbed and the other colors are being transmitted through the sample into the slit. So right here we're seeing these colors that are getting through, and the dark bands come from colors that have been absorbed. That's why this is called an absorption spectrum. And there's an exact complementarity between these two. Just to give us a little bit of practice with that, let's look at this example. So this is the spectrum that you see if you have mercury vapor in a gas discharge tube. You would get this emission spectrum. So this is emission. So which one of these 4 spectra, A, B, C, or D, would correspond to the absorption spectrum for mercury vapor? What would the absorption spectrum look like? So I'll give you a moment to think about that, and then I'll tell you the answer. Okay, did you come up with one? If you said C, then you would be correct. So notice how this line right here matches up with this dark band right here. Similarly, we have this triad, it looks like, of 3 yellow lines up here. Kind of matches these 3 dark bands right down here. Similarly, there's a big dark band down here in the blue-violet. That matches up pretty well with this dark blue line that's up here. So an absorption spectrum is kind of the opposite of an emission spectrum. Where you see lines in the emission spectrum, you will see dark bands in the absorption spectrum. Well, now this experiment, these sets of experiments, give us some idea of what might be going on then here with these Fraunhofer lines that we get from sunlight. So it's now understood that these dark bands come from the absorption of the sunlight at the surface of the sun by different elements that are present in the sun. So in fact, we can kind of look at the patterns and figure out what elements might be present in the sun. So this is how we know something about the elemental composition of stars. In fact, this pattern of lines from helium was first identified in the Fraunhofer lines. So we discovered the element helium actually on the sun before we discovered it here on Earth. In fact, the name helium comes from the Greek word helios, which means sun. So what is all this telling us? Well, it's telling us that there's something very interesting going on with elements and the way they interact with light. So apparently different elements like helium, hydrogen, neon, sodium, and really any other element has a very unique absorption and emission spectrum. And it's also very distinct. So the same colors of light that get emitted are the same colors of light that get absorbed, and it's not all colors, it's only very select colors that get emitted and absorbed. So this must tell us that there's something very special about these atoms and different about these atoms of the different elements that cause them to interact with light in these different ways. So all of this must be a clue as to the nature of the structure of the atom. And that's why we spent a little bit of time looking at some of the physics of light, because this is going to be a tool that will help us begin to understand the atom. So why is it that we only see lines? Why is it that we see these dark lines and complementary absorption and emission spectrum? Well, to figure that out, we need a little bit more information and a little bit more experimental results. We're going to go and look at one other very interesting pattern before we go on, and this is in the late 1800s. This is due to Balmer and Rhydberg. Now, Balmer was a Swiss mathematician and school teacher. And what we have here is a hydrogen atom emission spectrum. And so what you can see is when we pass the light through the prism, we get these different bands of color that show up. So there are 4 that are shown in this picture, and there's one really faint one that you might be able to see right there. And so here they are, and they're measured in wavelengths. Now what your eye may or may not be able to discern is that there's kind of a pattern here. You see how the distance between these lines seems to be shrinking down? Well, Balmer noticed the same thing, and being a mathematician, he started looking at these numbers, and he started wondering if there was a mathematical pattern to these lines. And because he was a very bright fellow, he was able to find such a mathematical pattern. This is called the Balmer equation. And using this, lambda is the wavelength, and so that's how he could calculate what these different numbers are using his equation. So he said that lambda is equal to 364.5 nanometers times m squared over m squared minus n squared. Well, what are these values? Well, Balmer found that if you take n equal 2 and then m equal 3, 4, or 5, that you could get these different lines. 3, 4, 5, 6, that you could get these different lines. So these 4 lines. And Balmer even suggested that if you stick 7 in, you would get this other color, this other wavelength, that had not been observed yet in his day. So nobody had seen this one, but Balmer predicted it was there with his equation, and lo and behold, it was found. So this is interesting. Here's a nice, simple little equation that lets you predict the colors of these light, the color of this light. So it's a mathematical pattern. We don't know why it has this mathematical pattern, but Balmer found that it fits the experimental data very, very well. Now later, Rhydberg changed this equation up a little bit. So he looked at 1 over wavelength, this way, 1.097 times 10 to the minus 2 inverse nanometers. So that's what the minus 1 means, is inverse nanometers. 1 over n squared, that quantity, minus 1 over m squared. And Rhydberg was able to show, because after this experimental work was done, there were other emission lines of hydrogen that were discovered over here in the infrared region, the IR, and some other emission lines that were discovered in this region, in the ultraviolet region. So it took some technology developments to be able to discover those emission lines, but they were discovered. And Rhydberg found he could generalize Balmer's equations to work for those lines as well. So what you do is you take n equal 1, 2, or 3, and if you pick 3, you'll get the same result of Balmer's equation. And then you take m equaling n plus 1, n plus 2, and so on to get the wavelengths of the different lines. So again, both of these equations are just mathematical statements that fit this pattern for the hydrogen emission spectrum. But a scientist looking at these patterns is going to say, Well, why these integers? Why this particular pattern? Wouldn't it be cool if I could come up with a theory, a reason why the structure of the hydrogen atom would lead you to these equations? And so that's where we're headed. Scientists begin scratching their heads and thinking about why this would be. So we get some other clues by looking at some other important aspects of light and some other important experiments that were done right about 1900. So here we're moving through time. And this is covered in section 7.3 of your textbook. We're going to look at particles of light and the beginnings of something called the quantum theory. So we're going to look at two important experiments, one dealing with something called blackbody radiation and the other one dealing with something called the photoelectric effect. So first, blackbody radiation. So long about 1900s, this was an important unsolved problem in physics. Now, there's a theoretical object called a black body that physicists talked about, but we can think about it this way. Imagine that you had a bar of iron, and you start heating up that bar of iron. What you'll notice that at first it gets warm, but there's no color. But then as you continue heating it, it starts to get red hot, right? And if you keep heating it, it will get yellow hot and on to white hot, maybe even bluish. So as you keep heating it up, the colors of that bar change. So what physicists in the day were doing was taking that light, and it was fun to pass light through prisms, so they would take that light, pass it through prism, and spread it out. Now by this point in time, they were able to somewhat measure the intensity of the light coming out at different wavelengths. So how much energy is carried by that light. And so what's plotted here in this graph are some of the experimental results for wavelength, so that corresponds to color, and the log of the emission intensity. So we're going to take the logarithm, the base 10 logarithm, of that emission intensity that I told you we're measuring. So you can think of emission intensity as just being related to brightness. So the brighter the light that you see, the more intense it is. And so what we're really doing is a plot of brightness versus wavelength. And what you see is we change the temperature. So here we are at the lowest temperature of 300 Kelvin. That's kind of close to room temperature, 25 degrees Celsius. And you see that most of the light being emitted from an object at that wavelength are really long wavelengths. So these are way out in the IR region. So if we happen to have eyes that could see in the IR, then we would actually be able to see that light. And in fact, some night vision goggles do that. They amplify, they let us see into the infrared and amplify that light so we can see the light given off by warm bodies at night. So as we begin to heat this sample up and move up to 500 Kelvin, what we notice is that the colors shift. So right here, this peak, I'm drawing right here, that is the highest intensity, and that occurs for 300 Kelvin at a wavelength of about 10 nanometers. So there's still light given off at other colors, but just not as much, so it's not as bright. But once we move to 500 Kelvin, the peak has shifted here to shorter wavelengths. So shorter wavelengths are bluer in color. And as we continue heating this up to 1000 Kelvin, we begin to start seeing a little bit of low intensity, so not very bright, but in the red region of the spectrum. So we could actually see that with our eyes. So it's beginning to glow red hot very faintly. But as we continue heating it hotter and hotter at 2000 Kelvin, then we've got a lot of intensity all over the visible region. So we might start seeing yellow hot or white hot light. And then at this temperature, 6000 Kelvin, which is approximately the temperature of the sun, the surface of the sun, we start seeing lots and lots of intensity here in the visible region. It's no wonder that the sun at that temperature gives off light of this color, and that our eyes have somehow evolved to be particularly sensitive to the maximum emission intensities, the brightness that's naturally given off by the sun. Isn't that nice? So we see as we heat an object up, we start getting more and more light at higher intensities. So the reason this was an interesting problem to physicists is they were trying to understand this relationship. Oh, by the way, you do see that color emitted corresponds to temperature pretty well. This is the basis of some technology that we use called optical pyrometers. So an optical pyrometer, optical means visual light, using light, and pyro, you know about pyro, that means related to heat. So we can use these devices, point them, aim them at a particular object, And even from a pretty good distance, they could tell us what the temperature of that object is. So they're just using these wavelengths that get emitted and relating those to temperatures. This is in fact the kind of thermometer that are often used to measure the temperatures, say, of animals or very young children who don't take thermometers very well. You can just put this in their ear or touch it to their forehead, and you can measure their temperature. So optical pyrometers have a lot of important applications. And in fact, you can connect your pyrometer to the back of a camera and actually take images of things like motors or systems and tell where those systems are building up heat, measure the temperature at different points on an engine by looking at that image. So there's this connection then between temperature and color. Well, physicists back in the 1900s were trying to understand this, and a physicist by the name of Max Planck was trying to tackle this problem. And physicists previous to that had used known physics, the laws that Newton had laid down and the laws for light that were laid down by Maxwell, trying to solve this problem, and they kept getting nonsensical answers, so results that didn't make any sense to them, so they could not generate these theoretical curves. So Max Planck was able to reproduce this experimental data, all these curves. He was able to come up with equations that show the relationship between wavelength and temperature and fit these curves very well, but he used a very radical idea. So Max Planck said that in order to think about this correctly, you had to use the idea that energy, the energy of the light and the atoms in the substance that you're heating up, had to be quantized. So what does this word quantized mean? Quantized just means that it comes in very specific fixed values. So it can't take on just any old value possible. It has to be a fixed value. Now this is a very curious idea. So let's think about our formula for kinetic energy that we saw back when we were looking at gases and the kinetic molecular theory. So 1/2 mv squared or mu squared, where u is speed, m is the mass of the particle. So we see that if a particle is traveling faster and faster, it will have a greater and greater kinetic energy. So kinetic energy in this case can take on any value that it wants. So if we're plotting energy here on this axis, and let's say a particle has this amount of energy, and we wanted it to have some other energy up here, well, it would be easy to get that to happen. We just make the molecule move faster. But because we can make the molecule move any speed we want, we can have that molecule take over any energy at all in between this gap. So we say that energy is continuous in this picture. So it looks like energy can be absolutely any old value you want because an object can move at any old speed it wants in between this range, and actually above this range and below this range. So energy would appear to be continuous. But Max Planck comes along and says, hey, to get the right answer with my equations to fit this experimental data, I have to say that the energy contained in these molecules and the light comes in only fixed packets. And he used a term for that fixed packet of energy. He called it a quanta. That's supposed to be Q-U-A-N-T-A. So quanta. So he called that a quanta of energy. And that's the smallest amount of energy that you could possibly have. You can't subdivide it. You can't chop that up into a smaller amount of energy. And so Planck was able to calculate that the energy of these quanta of light, and he actually, Einstein, a little bit later, we're going to talk about him soon, described the quanta of light, or the particle or packet of light, as a photon. And Planck said that the energy that a particular photon, the smallest particle of light that you can have, is given by this equation, some constant h times the frequency of that light, nu. So nu is the frequency, and h is a physical constant, so a constant of the universe. It always has the same value. And today we have measured this value in SI units as 6.636 times 10 to the negative 34th joules times seconds. And so that's the value of this constant, and this constant is now called Planck's constant, after Max Planck, who first came up with this idea. So this is Planck's constant, h. So this is a very important equation. It tells us about the energy of the smallest packet of light that you can have. So if we have brighter light with more energy, that means we have 2 of these packets or 3 of these packets, but we can't have 1.5 packets of energy. That's what Max Planck said. Now again, Max Planck kind of agreed that this was a crazy idea, but this is what he needed to do in order to get his equations to match up with experiment. And this is the interpretation that he gave to his theory. So he introduced this new idea that energy might be quantized and come in these little fixed packets that he called quanta. And that's the smallest amount of energy that you can have. So if light contains energy, then we can think of this quanta of light, this photon, as Einstein called it, of light, as being the smallest packet of light that you can have. So Einstein, it turns out, I was just talking about him, was interested in explaining this effect. So Einstein did not do these experiments, but he was interested in thinking about them. So Einstein, back in 1905, was looking at a theory to explain this effect. It's called the photoelectric effect, and it had been known for a while. And if you take a certain piece of metal and you connect it to a battery, a voltage source, and you shine light at it, so here's our metal, and it's connected to some voltage source, and then you have incoming light, that if that light is of the right frequency, you can knock an electron off that metal, and that electron can then be picked up by some sort of positively charged metal plate over here that is also connected to our voltage source, and that will create a little tiny electrical current that you can then measure. So this is called the photoelectric effect. So from incoming light, photo means light, so light coming in, electron gets knocked off, so that's where the electric effect part comes from. So light generates electrons. We knock electrons off. Now there's something very interesting when you do this experiment. So here's the way that this experiment might be set up. Here we have a glass tube, and it turns out to get this experiment to work very well, you have to evacuate the air because the gas molecules will absorb these ejected electrons. So you make this a vacuum inside this glass tube, and then here's your metal surface right here that we were just talking about, and you plug that into the negative terminal of some voltage source. So here's a voltage source, a big battery. And then you have a little electron acceptor right here that builds up a positive charge. So it's connected to the terminal of your battery that will generate a positive charge. And then when light of high frequency shines onto that metal surface, electrons will begin to be emitted. They will fly across this gap, intersect this little rod. Those electrons will travel down into your voltage source and through your little meter here, and the meter we can use to measure the electric current that is flowing through this circuit. Now if you turn the light off, the meter goes dead and there's no current there's no current passing through the circuit. Turn the light back on and you get the meter reading, so we have current flowing through the circuit. Now what's interesting about this experiment is if we change the experiment so that we're using low frequency light instead, that what you see is you get no current out of your meter. So even though light is shining on it, you can even turn the light up, so have really high intensity light, really, really bright light, but still low frequency light, so like red colored light. So high intensity but still low frequency light, and you still get no current out of that experiment. So what Einstein said is that there must be some threshold frequency. So we'll label that nu sub 0. That's our threshold frequency. And this is borne out in an experiment. So if you have at least that frequency, then you can start generating current. If you have a higher frequency than that, you'll still generate the current, but any lower than that, no current. So Einstein associated that with the energy required to pull an electron off the metal. He gave that the symbol capital phi, that's the Greek letter phi, P-H-I. This is the capital Greek letter. And he called that the work function of the metal, because this is related to the amount of work that you would have to do to pull an electron off that metal. And so you have to put in at least this much energy, and then you can yank an electron off that metal. If you don't have that much energy, then that electron is going to stay attached to the metal. And so Einstein based his theory on the work of Max Planck, and he said, okay, I'm going to say that you have to have this much energy. So I'm going to take Planck's constant, and I'm going to multiply it by this threshold frequency, and that's going to give me the work function, the amount of energy that you have to put in to remove an electron. Thinking about this, Einstein modified Planck's equation, so sometimes this is called the Planck-Einstein relationship, to calculate the energy of a photon. So he said light then has this energy. Planck's constant times frequency. And because we know that frequency of light is equal to the speed of light c divided by the wavelength of light lambda, we can rewrite this equation in terms of wavelength. So the energy of a photon in terms of wavelength is equal to h, Planck's constant, times c divided by the wavelength lambda. So either of these two equations will allow us to calculate the energy of 1 photon's worth of light. So here's a little bit more data from the photoelectric effect. So what we're going to do here is we are going to vary these experimental parameters. We're going to vary the light intensity and vary the light frequency. And then we're going to measure these two things. We're going to measure the electric current, just using that device that I talked about. We're also going to develop some sort of special experimental technique to measure the kinetic energy of those electrons that are coming off. So if the light intensity is low and the light frequency is very low, then you get no current, and of course there's going to be no kinetic energy of the electrons because you're not knocking any of them off. So if we go up and we make the light intensity high, right, so shining very bright light but still very low frequency, then again we see that there's no current and of course no kinetic energy. So now we're going to go back to low intensity light, but now we're going to make the light frequency low. But even though it's low, it's high enough to exceed that threshold frequency, nu sub 0. And then we start knocking off those electrons. So we start seeing a little bit of current, but it's kind of low, so we don't get very much of it. There's a kinetic energy for these electrons too, but not very much. So they got ripped off the metal now that we're past this threshold frequency, and they're low kinetic energy. So now what we're going to do is ramp up that intensity. So now we have really high intensity, but we're going to keep that frequency low, but still above the threshold frequency. Now what we see is the current is high. Our needle goes really, really high for current, but the kinetic energy of those electrons that gets ejected is still pretty low. So let's do another experiment. Let's make the light intensity low again. It's a really dim light, but now we're going to really ramp up our frequency. So now we've got really a frequency that is much, much greater than our threshold frequency. So what we see is that the current, though, is still low, but now the kinetic energy of those electrons that have been knocked off, it's really high. Those electrons are moving screaming fast. So what happens if we ramp up the intensity, still keeping the frequency very high? Well, now we have both high current and a high kinetic energy. So Einstein was able to rationalize all of this by saying the photon comes in with a certain amount of energy, right? So the energy of the photon comes in. So we're going to imagine that this is a little packet of light. So I'm going to draw it kind of as a little energetic blob. So it has it's a little particle of light. So it's a little minimum packet of energy. So the energy of that photon, then when it hits the metal, it goes two places. First, it goes to ripping the electron off of that metal surface. So that's the work function. And then any leftover energy is going to go into the kinetic energy of the electron. So the number of electrons that then get emitted, knocked off, released, is going to be related to the number of photons that we have coming in, or the intensity of the light. So if we have really bright light, so if our light intensity right here is high, we have lots of photons coming in, many photons, and then we get many electrons released, which results in a high current. So let's check that out. Whenever our intensity is high, as long as we are past our threshold frequency, we end up with high current. So that agrees. Now we can think about what's going on with the frequency. So if our photon has this amount of energy, Planck's constant, times the frequency of the photon, then that energy goes two places. First, we have to put it in to rip off our electron. Any leftover energy goes into kinetic energy. So let's look at if we have high frequencies. So if we have high frequencies, so this number is big, that means that the energy of our photon will be big. So we'll need a little bit of that energy to go in and knock the electron off the metal. That's the work function. But then we'll have lots of excess energy to give to that electron, so it flies off very fast. And that means it's going to have a very high kinetic energy. So notice in these cases where we have high frequency, both high frequencies, the kinetic energy of our electron is very high. But if our light intensity is low, then we don't have very many photons coming in, so this number would be low. And so the number released is low, and we're going to end up with a low current. So Einstein's idea then explained all of these experimental results. But it creates a really interesting idea. So both Einstein and Planck's experiments seem to suggest that light has properties that make it look like a particle. So we've been talking about packets of energy. So what we know about particles is that they come in lumps, right? Little lumps. Well, that's what it seems like light is doing. It comes in little tiny packets of energy that can't be any smaller. So the energy of that light arrives in a lump, and that's a property of particles. But we also know that light has properties of waves. So if we do other kinds of experiments, we see that light can bend around corners. Particles don't so much do that. Lights can also be diffracted when they pass through a slit. Again, that's not something that we really associate with particles being able to do. So what is light? Is it a particle or is it a wave? Those seem like pretty different ideas, right? Waves spread out in space. Particles are little lumps that occur in a particular location, right? Little lumps that occur like this little dot that I've made. So what is it? Well, it seems, based on these experiments, that depending on the kind of experiment you do, light can behave either as a particle or as a wave. And we call that particle-light duality, and it seems to be a property of the nature of light, albeit a very weird property. And physicists were very confounded by this, but it seems like the right theory to explain both the photoelectric effect, blackbody radiation, and, as it will turn out, a host of other properties.